In this video, we're going to look at a detailed example of punching shear using Adapt Builder version 20, and we're going to do this for a two-way flat post-tension slab. We'll go ahead and launch Builder version 20, and we're going to make sure that we have the proper assignments for the different modules here. So we want to use Floor Pro. This is primarily for elevated slabs with or without beams. We want to have the PTRC mode selected. This allows us to model the actions and essentially the objects representing post-tensioning cables. And then we're also going to look briefly at a difference between a single level run versus a multi-level run as it relates to post-tensioning. So these are the different options we'll be using in this tutorial. We'll go ahead and just start our model. We're going to open up an existing model here. And we'll notice if I switch this, we're now working in plan mode, but if I switch this over to a 3D view, we're working in what's called single level mode. So if we analyze this particular model in this mode, we're really only analyzing this level with some assumed support conditions at the bottom and the tops of walls and columns. If I look at a multi-level view, we have really a multi-level structure here, and I'm going to go ahead and change the visibility to a solid shade so we can see that a little more clearly. So we're going to look at a difference between multi-level and between single level. We're going to start here with single level, and if I select the tendon option to show my tendons, we're going to select a level that already has post-tensioning included. So several of the levels at the bottom of the structure are similar. So here we have some PT. We're going to focus primarily over here on this left-hand side. Before we actually start the analysis, let's define some of the inputs for punching shear. Now, for this particular column, I'm going to create another opening here. So let's go to model, and I'll go to opening, and I want to create just some abstract opening there. Notice that if I reset the shading, it goes and updates the view of that opening. If you compare this version to previous versions of Builder, several of the global settings that were in previous versions have now been transitioned over to local settings. For example, if I select this column using the property grid, I'm going to go ahead and collapse everything and then just open punching shear. There are different settings here that were once global settings. They apply to every column that was being checked for punching, and now we can isolate and apply different settings to each individual column. So I'll define the settings here that are related to individual columns. We'll call these localized settings. I'll define these, and then I'll go to the floor design option under shear design, and these are what we would consider as global settings. We'll define each one of those in detail. So the method is either auto or user. Auto means that the program will categorize the column based on the algorithm being used to do so. And for example, the program will check from each column face the distance to a slab edge. So in this case, we're checking at a distance 4 times the slab thickness we'll call H. And if the program sees that that falls outside of a slab region, it assumes that that's a free edge of the column. So in this case, if this distance, I'll call this distance here, we'll call this the negative X side versus the positive X side, or if we're using local coordinates, this might be the negative R side versus the positive R. This is positive S and negative S. And we'll stick with those coordinates because they're actually referenced back here in the property grid. So this distance on the negative X face of the column is, let's assume that that is less than 4 times H. So what that means is the program ignores automatically that distance. So the program categorizes this as an end edge column, and it assumes that this is the free edge at the back face of the column. Now that can be changed per a global setting that I'll show you later, but this means that the program says that this is an end or edge column, we have a condition where we have side 1, 2, and 3. So this is a three-sided critical section that we're checking. This is, again, categorized as end or edge, and that's actually shown in the results graphically or in the tabular results that we can output for the punching shear check. If I look at a column like this that's interior, we ignore the presence of openings in terms of the categorization. So if we look this direction or this direction, these all fall within the slab. This would be a four-sided critical section. This would be an interior condition. And then we also would have a corner condition. Here, this distance on the positive S side and the negative R side are outside of the slab edge. So here we would assume that this is a free edge and this is a free edge and this is now a two-sided critical section. And the centroid of that critical section is actually maybe here, which is eccentric to the centroid of the actual column. And so the moments generated due to that eccentricity and the axial load in the column are considered in terms of the flexure being transferred through shear of the column. That's the same thing that happens over here when we look at bending here, which this bending about, let's say, a S-axis would be an end condition, bending about the R-axis would be the edge condition. So that's how those are treated. Now, if the user wants to manually assume something different other than what the program categorizes, we could change this to user. And when you go to user, the program, let's say that we have this internal column, but for some reason we want to ignore the positive R face. So we could say the only faces of the column or the sides of the column that we want to consider are really going to be the negative R, positive S, and negative S. And we can go ahead and turn those on. The program ignores this. So this actually gets checked like an end edge condition by user modification, not by automatic selection of the case. One thing that might be helpful is actually, and this is also new in version 20 in the property grid here, but you can go to the general properties of the column and select display local axis to show the sides of the columns that were being considered that are being considered here. So that's what this is for, user versus automatic. I'm going to go back to automatic for our example. Pre-compression, when we have a post-tension slab, there is a component of the allowable stress that is related to the pre-compression. It's usually 1/3 or 0.3 times the average pre-compression in the slab. And in previous versions of the software, ADAPT's methodology was such that it would baseline to the low level of pre-compression using 125 KSI or 0.85 MPa for pre-compression. The program now allows the user to set that value to a user-defined value, either higher or lower than what the previously hard-coded value was. And so this, if a user went through the process of generating, let's say, design strips, and for these design strips, if I go here to floor design, let me just turn on the results here, see if we have results for this particular location. If I look at the stresses, I can see that the pre-compression at this column face is actually 92.8. That's through FEM usage. That means we're taking the axial stress that's integrated on that line over the area of the cut. So this is 92 and 85, and then in the other direction, if I just toggle this to the Y direction strips, I get 168, 125. So the user can make some judgment as to what value to use for that pre-compression input aside from just using the default 125. So that's what that's for. The reinforcement type is studs or stirrups. So if you use studs, then you would select the diameter of stud that you wanted to use in the pull down list here. If you use stirrups, then you get again a bar diameter here that's equivalent to a number of bars, let's say, for reinforcement. So studs or stirrups are the two different reinforcement types. The user can now set the number of rails per side individually. So that's shown here as R or S. In previous versions, the number of rails per side was applied to all sides. So for a rectangular column, that doesn't make too much sense. We might need 2 and 4, 2 and 3 configuration in terms of rails. There was an option added in version 2018 which allowed the program to check and make sure there were enough rails to meet 2 times effective depth spacing along the periphery of the column sides. So that was kind of a bypass to having equal number of rails per side, but here the user can specify that directly for any individual column. Spacing of studs, we have uniform or calculated. And this is important to understand in terms of what does this do to the output of our column. And I'm going to describe this here in just general terms. And let's take this column for example. Now this column, if we're checking punching shear, the way that the program checks punching shear is it will take critical sections at some distance away from the column face and then at additional layers away from the previous layer. So these spacings are d/2 conservatively. For post-tension slabs, we can use 0.75d for those layers away from the first layer from face of column. That has not yet been implemented, so conservatively we're still using 0.5 times d. But what happens is the program will check these layers, and if it finds that there's reinforcement required for each layer, the program adds that reinforcement between, for example, the column face, and we'll call this layer 1, 2, and layer 3. And so the amount of reinforcement needed, or the number of studs needed between face of column and layer 1 might be, let's just say three studs between this face and this face. And between layer 1 and 2, we need maybe, let's say 2 studs. And between 2 and 3, maybe we need 1 stud. And let's assume that these number of studs translates to some spacing of those studs within the layer. So let's say that the spacing here is 1 inch. We need more studs, therefore the spacing between face and layer would be smaller. If it's 2 studs, let's say this is 1.5 inches, and then this is 2 inches, or let's say 3 inches. So the output for a column under this condition, if I go back to that output, the spacing of studs uniform versus calculated, this would be the calculated output. The way the program would present that, which we'll show later, would be such that it would say, okay, we need 3 studs at 1 inch, we need 2 studs at 1.5 inches, and we need 1 stud at 3 inches. Now, being able to translate this into drawings and making this usable and constructible in an efficient way, that's a separate story. We might want to uniformly represent these studs. So we have multiple columns that might fit into a scheduled layout for studs or for stirrups. And so if we select uniform, what the program will do is it will say, well, we're going to take the total rail length. The total rail length by calculation for this configuration that's calculated would be 3 inches plus 3 inches plus 3 inches plus some edge distance. So let's say that that's just 10 inches. That's the total rail length for this calculated configuration. If we convert that to uniform, the program takes the least stud spacing out of any of these ranges, we'll call them, and that's 1 inch. And it takes the rail length divided by the least spacing, 1 inch, and that translates to 10 studs at 1 inch spacing. That's the uniform output. So you can see that becomes a greater amount of studs than the calculated. The calculated was 3 plus 2 plus 1, that's 6. This is 10. So you're going to always get more studs using the uniform arrangement than you would using calculated, and that's because the program is simply post-processing the output results versus running the solution again, assuming some uniformly spaced arrangement of studs. That is coming in a previous or in a later version, but currently that is how uniform spacing is being calculated in the program. It's post-processing the output that's already been done per the calculated method. The next option here, reduction of critical section. So this is always on auto. This just means that if you have openings in your model and they're active openings in the model, the program is going to consider them if they fall within the tolerance range that I'll show you here in a moment. This total angle relates back to the openings also. So we'll talk a little more about that. Now, if I kind of transition over to those were local settings for punching shear, and I'm going to transition here now to global settings for punching shear. Some of these global settings have been legacy settings in the program for quite some time. It has been recategorized in how they're presented back to the user, so we'll talk about that. And I'll kind of mark the ones that have been historically located in the program. So the ability to design for moments separately versus combined, that's been there for several years now within the program. This just means that we check stresses individually for bending about the two different axes versus combining the stress. Consider critical sections outside the face or outside the shear reinforced zone. We'll talk more about that here in just a moment. I want to jump down here to extend critical section to slab edge. We'll come back to the two above that. So earlier I showed in the model that this here would probably be categorized as an end edge condition, and we would assume this is a free edge. So we're not really even counting that the failure mechanism would actually break through this free edge, the true free edge of the slab, if this was to fail in two-way shear. So what the option that I just showed, extend the critical section right here, extend critical section to slab edge, that just means the program would include this portion on the negative R side in the allowable stress or the resistance length for that particular critical section, and every other critical section would also extend past this virtualized free edge as well. So that's what that option is for. It is a global option, so if you enable it, it applies to every column that kind of falls under that condition where the edge distance to one or two sides is within the 4 times the slab thickness. Okay, limit rail spacing to 2 times effective depth. Now this, again, the user has the ability to specify a number of rails on either side. So if we take this column, for example, that we're looking at, this means that we're going to align 3 columns, or we're going to assume we have 3 columns at each face. If this option is checked, the program will check the spacing between the rails on both sides, and if that spacing is less than or let's say greater than 2 times effective depth, the program will add a 4th rail automatically, and that will be shown in the outcome of the result. If this number is greater than the requirement being checked, the program defaults back to the user-defined number of rails. So that's what that option will do. If you don't meet that option or that requirement per your settings, then you'll see that the program adds an additional stud rail on, typically 2 sides of the column that are of equal length. Okay, let's talk here about openings, and I'll jump back up here to these two. So openings is new to version 20, and the program has been completely revamped in how it looks at openings. So let's say we have these 3 openings that are near this column. And we're going to go back, let me come back to there. And we have a radius of detection and a maximum reduction per face of support. So the radius of detection just says if these openings are within, or they intersect, that's not a perfect circle, but let's assume that that's a circle, and these openings are within that circle or they are intersecting that circle, which is a function of the slab thickness. It's a user coefficient, user-defined coefficient. The openings are considered in the check for those openings as it relates to punching shear. So you have the ability to check that right here. The next thing is the maximum reduction per face of support. Here we say it's 90%. And so what that means is that if I look at this set of openings a little more clearly or in more detail, let me turn off the local axes. What's going on here is the program is actually taking a virtualized construction rays, and it's taking these to the outer extreme limit or the outer edges, let's say, of the openings. So these are the construction rays. And the program determines the length. So I'm going to use a different color here. There's a length here between these two rays, 1 and 2. There's a length along this face between rays 3 and 4. And then there's also a length along this same face between rays 5 and 6. The program will determine the length of each one of these. So this length, I'll call this L1, we'll call this L2, and L3. If L1 is more than 90% of this side, so this is the positive R face, if L1 is greater than positive R face times 0.9, then we assume that we assume this is a free edge. We ignore this side. If on the negative R side times 0.9, that's the factor we've input, if L2 plus L3 exceed 0.9 times this negative R face, then we would ignore this side. And that leaves us in a kind of a strange condition in terms of punching shear, but that's what's happening. If you have so many openings where you're intersecting the column face such that you really have nothing left there because there are so many openings, we just ignore the side. That's the input for that reduction, and that's shown here, max reduction per face of support. Now, if I come back to my rays here, let me just clean up some of these things. The program, when it actually creates these rays, and earlier I mentioned we have these kind of critical perimeters working around the column. You know, if I have layer 1 and layer 2, we're going to discount this distance, you know, passing through the opening for that particular layer. We would discount this distance from here to here. And then for layer 1, we would discount this distance from here to here in terms of the critical length of that particular layer or critical section that we're working with. So that's how the openings are considered in this new version of Builder, which is, again, Builder version 20. Okay, so that should define those options. We have 2 more things to define. Consider critical sections outside the shear reinforced zone. Then we have this edge distance input. And in previous versions of the program, prior to version 19, the program always used rectangular or square critical sections. So we would just check this column, you know, until we needed no additional reinforcement and until the stress was less than 2 square root of F prime C, for example, for US-based ACI methodology. And this new option means that once the program determines using a rectilinear critical section, let's assume we get to critical section 3. And at this critical section, we find that there's no reinforcement required, meaning the allowable stress is greater than the actual stress, and we just, by calculation, we need no reinforcement. So at that location, we convert this section, this critical section, we convert it to a to the least critical section, which in this case would be an octagonal shape, assuming our rails are laid out orthogonally along the column like so. So the least critical section for layer 3, this is layer 3, we check that as a rectilinear section and then we convert it. If we find there's no reinforcement, we immediately convert that to this shape. And we then check the stress on that critical section. If that stress and the edge distance is used to determine, these leg lengths, the edge distance from the edge of column to the rail center line. So for this pink critical section, this reduced critical section, we check the stress. If that stress is greater than 2 squared of f prime c, then we basically continue to use that critical section shape, and we grow that until we reach a limit of 2 squared of f prime c or less. And we add additional reinforcement on the rail as this grows out once we transition from the rectilinear to this octagonally shaped critical section. So that's what that is for. If you do not select that option here, if you leave that turned off, then the program continues to just check per the legacy method, which is using the rectilinear critical sections. The last option is apply minimum reinforcement for drift. And this applies to the ACI code, and there's a provision there where based on some drift checks and let's say allowance for drift, if we exceed some threshold, we have to apply minimum reinforcement for punching shear, and it has to be such that the allowable stress, or the stress given by, or the strength given by the reinforcement, is greater or equal than 3.5 squared of f prime c. And so the program would also apply that requirement if you select this option. And both of these options, if we go up here to our documentation, if we go to documentation and look at the new release feature supplement version 19, okay, these were actually introduced in version 19. Those are both described in this document for punching shear. So if you go under the punching shear section 2.6, we describe critical section outside reinforced zone and minimum reinforcement for drift in more detail. And some of the code references are there for those provisions and the way that ADAPT has implemented them into the software. So let's go ahead now, and I'm just going to leave the settings as they are. I will turn on this setting. I'll leave the minimum drift setting off, and we're going to now run the model for punching shear. Now we don't have to design sections for punching shear, and I'll describe that here in a moment. This is going through that opening that I added. I'm going to go ahead and just move that, and you'll see it. I have a tendon that has to kind of weave around these two openings. So this is a good example of using a spline tendon. If I use a spline tendon, what I can do is on this span we have a low point here. This is a low point, and we have a high point and a low point, and that's indicated by this green symbol that represents a high point. If you set it to a spline, the blue is always a low point. So if I take this span here and I just insert a couple of swerve points, I can actually move that cable around that opening like so, and I could kind of move this one back in if I insert swerve points, maybe there and there. So this allows you to modify the in-plane sweep of a cable without having to adjust the vertical profile of the cable in the program if we convert it from a linear to a spline cable. So that should fix that problem. I should be able to go back now and mesh the slab. Okay, and so here we have our mesh. We're going to run the analysis. I'm just going to run this for strength, dead, and live, and strength, dead load only. So for punching shear, we only check this for strength combinations, those combinations set to strength. And that's done under loading and load combinations. There's a way to tag the combination type to a specific purpose. In this case, we're designing for strength. So let's go ahead and now look at these actions. So the way the program utilizes the actions, I'm going to go back to our wireframe here for a moment. For this column under the combination, let's say strength, dead, and live. This produces the highest moment and the highest axial force. So if we look at the actions for the combination axial, this is actually the force that the program is going to be using to check punching. So this is the direct shear, and we'll use that force to determine what the shear stress is on the critical sections. And then for bending, we'd be looking at the moments. This is moment about the R local axis. If I come back to here and turn on the local axes, this is bending about R, 79 kip feet, and bending about S is about 28 kip feet. So if you're ever wondering where the numbers are coming from, it's coming from just the analysis results and the actions that are being calculated for that particular column location. After we analyze, we can then go directly and run punching shear. So I can go here to execute the punching shear check. And there are two kind of groups of results. There's tabular results, which include Excel outputs, and also the graphical results. And I'll first talk about graphical results. So I'm going to turn off the actions and clean that up a bit. And I'll go to loads. We want to make sure we either have a strength individual combination selected, or we have the envelope selected. If you have service selected or service envelope, you'll notice the punching shear gets grayed out. It's inactive. We have to make sure we have strength selected. So I'll go to the strength dead and live case. And we're first going to check status. This just tells us if the column is okay, if it requires reinforcement. If there's if it exceeds code, that means some critical section we exceed the maximum allowable stress, 8 squared F prime C, for example, for a PT slab, or not applicable. Like these walls, we're not checking punching. Anything NA means we haven't checked the punching for it. So this column doesn't actually require reinforcement. We'll go up here to this one and look at the reinforcement there, but you can see it says it's okay, and that doesn't really tell us a whole lot, just gives us a status check. If I go to stress ratio, you can see the program reports the controlling ratio for the R axis and S, and that's because we're checking the moments about the axes separately versus combined. If you want to reduce the font height here for this text, you can go to the view settings here for column, and I'm going to just cut that in half, for example. Okay, so the ratio is 0.7 and 0.65, and this CS is for critical section 1. That means that at the first critical section, that governs the worst case ratio, critical section 1. If I select the envelope of strength, there's an additional thing added. Global load combination 3 controls at critical section 1. So global load combination 3, or governing load combination rather, is really in sequence what is the third combination, and the third combination is strength, dead, and live. The first two combinations are actually service related, so those are not being checked. The third combination is, and it actually indicates what that combination is up here. That's combination 3, strength, dead, and live. So there are a couple of new pieces of information that are related to the column for punching shear when you select the stress ratio. Previous versions did not give any indication where this ratio is coming from. This version obviously does that. And then we have condition. This tells us how it's being checked, and you can see over here on this side, there's that free edge that we talked about earlier for that column. And coming back to the shear design, we did not extend it to the slab edge. So this is a pretty conservative check for that, for those columns on the perimeter where we have this little cantilever hanging off the side. But this just kind of color codes the critical section. The effective depth is reported. This is just the first critical section's effective depth is reported here, 10.38 for that first critical section. So this just shows really the first critical section from face of column. And then ultimately we get the reinforcement. This shows acceptable. We don't need any reinforcement. And if we look at this column here, we do need reinforcement. So let me just see if I can bump up the font here for these results. Okay, so this needs no reinforcement. We'll talk about the reinforcement here. And what this says is we have 3 and 3, 3 rails along R, 3 rails along S. There's 1/2-inch diameter studs, and we're looking at uniform spacing of studs. So what this means here, the nomenclature is we have basically a 1/2-inch diameter stud. We have 12 total rails, and we have 3 rails on the R face and 3 rails on the S face. So we have 3 rails projecting from the R face. The arrow would indicate a direction of reinforcement, so we need 3 rails on the R face, 3 rails on the S face, positive and negative. We have the arrow indicating the actual true length of the rails. Those are to scale. And we have 4 studs at 5 inches on center on each rail. And so the total length of the rails is 20 inches. And that's how that can be interpreted in terms of this output. So if we wanted to go further, you can see some of these columns need quite a bit more reinforcement. This is the rail length for this column, and this is just a 2-sided critical section. So in this case, we have, again, 1/2-inch diameter stud. We have 6 total rails. So we have 3 here on the positive S face, 3 on the negative R face, and there's 26 studs at 5 inches on center. There's a 130-inch long rail. If I convert this to a calculated system, for example, and I'll go back and just execute the punching shear again, you can see potentially a difference in the result. Now, the spacing could be such that it's equal through each layer, and that wouldn't really be known until you check it. So there is a condition where the spacing of a calculated versus uniform is identical, and this looks like one of those conditions where these are the same, regardless of what you select there, even here as well. But that's something that a user may want to check to see what the difference is and to what extent you have more studs if given a uniform condition based on the description of how that's being calculated that I provided earlier. So this is some of the graphical output that you can achieve through use of this result browser in the program. Now, additional things that we can report under reports and punching shear. We have parameters. These are, again, legacy reports that the program has produced for some time. We have parameters, which the program will just show the different column locations, the condition by which we're checking them, effective depth, design lengths in the R and S directions, area, section constant, and then the gamma factor for contribution of flexure for the shear check. Those are just a few things shown here under parameters, and this is for the worst case critical section, just FYI on that. If we go to stress check results, again, this is another similar type of a report, but this gives us different information. So for the worst case critical section, that critical section controlling the worst case ratio, the program shows us the shear, the moments, the stresses due to direct shear and to flexural contribution, and then the total stress versus allowable stress with the stress ratio. And again, that's only for the critical section that produces the worst stress ratio for any column. And then we get into a punching shear reinforcement report. This will show us for each individual combination set to strength. So this would show us the column label, the ID, the number of rails per side, number of studs per rail, total rails diameter, total rail length, and the distribution of the studs on the rail for that column. Here's one where you can see potentially a difference in the way it's being calculated. So this is 8 at 5, 18 at 5. There might be some, these actually by calculation might be different, but they're both being rounded down to 5 for this particular output. So this is an example of the tabular result of the reinforcement, and then at the bottom here you get the envelope of all strength combinations. So this would be what the user would need to satisfy the design for each column. And finally, we have this XLS punching shear report. This contains information for every column for every critical section. So this is a pretty detailed report. We won't go through it too thoroughly, but I'll just indicate a few highlights here. So if we take a look at this column, this is column grid D2. This is called grid D2. And so we're going to find that column here. And this column, we have different tabs: critical section geometry. This is showing us this is an interior condition without a drop cap. There's only one critical section, so the program only checks here one critical section D/2 from face of support. That's what FOS is indicating. And the stress passes, so we stop the check. That's why you don't see any layers in addition to layer 1. This indicates D/2. This is the effective depth, the design length in the R direction, design length in the S direction, and design area, total periphery times effective depth, section constants, and then the gamma for bending about R and gamma for bending about S. So this would be indicated for every perimeter, every critical section for a particular column. One column that needed reinforcement was this column here. This is column grid E3. And grid E3, we can see this has 6 critical sections. So the program checks 6 critical sections for this column. And again, the geometries for those critical sections are all listed and shown here. If we go to stress check, we get just stress checks for each of the different combinations. So for grid D2, we have 2 combinations. That was the first column we looked at: dead and live, dead load only. We have the actions that are reported, the number of critical sections we've checked, and then the stresses for every critical section. So the report that I showed you that was a PDF gave only one set of data for the controlling critical section. This gives the data for every critical section in these reports. Area of still required. This just reports for each critical layer what the calculated area of still is. So for layer 1, we needed 1.45. For layer 2, we actually need 0. That means that at layer 2, we transitioned from that rectangular section back to the octagonal section, and that continues to grow out another 4 or 5 layers until we get below 2 square root of F prime C, which is layer 6. And so we need additional reinforcement. This is just minimum reinforcement that's being calculated for this column in the output. And you can see some of those other columns that required quite a bit of reinforcement. Those grow out to several different layers. There's 28 layers on column grid D3, and that was this column here. If I take that column and I convert it to this option to extend critical section to slab edge, that's going to reduce down the number of layers, because conservatively we are checking this with this assumption that we're ignoring, this distance to the edge of slab. So it'll reduce the number of layers and the reinforcement down somewhat, but the user would just have to go through that exercise of checking that. This shows us the reinforcement. So we have the area of steel. This is really a reflection of the enveloped amount of steel you see in this report. The number of studs is calculated for each critical section. So we need 1 stud between face and D/2. Then we need 0 studs. Then we convert the same critical section location to a reduced B0, and we need again 1 stud. And this just calculates that out until we meet 2 square root of F prime C. And so those show you the area of steel and the number of studs required per, this is really per rail, right, for that particular critical section, or the gap between the two adjacent critical sections. Stud rails, this is really just a reflection of the PDF report we showed earlier. And then stirrup schedule, this is blank. We didn't use any stirrups for this example. So that's a quick run through of punching shear in Adapt Builder. Now one thing I'd like to add in closing is, how does the program treat the actions when it comes to punching shear if we actually ran this in multi-level mode? So if I run this model in multi-level mode, what the program would do, I'm going to change this whole thing to wireframe, and I'll go ahead and turn this off. What would happen is the program would take, here's my column here, and let's say we have a, I'm going to just draw this, let's say we have this column and some level, and then we have another column. So I'll call this the upper column and this the lower column. We're actually checking the lower column for punching shear, and the axial force in the column is taken, the axial force that we design. Let's assume that this axial force is 200 kips, and the axial force here is, let's say, 150. So in terms of checking punching, the program would take, for any individual combination that's set to strength, we would say take the axial force in this column, subtract it from this column, and design for the difference between these two floors. That's the axial force that we would use when we calculate the shear for the direct shear through this column stack. For bending, we just sum the bending between the top. So if this bending diagram, looks something like this, then we have another diagram here that looks something like this. We would take this value plus this value and use that for the bending action for both directions. So we would do that same thing for the R direction, bending about R, bending about S, and those would be the actions that we use. Now, one thing to be careful of is, if you have a column like so, and you have another column that's stacked above it that's offset, so we have this gap, and this gap is outside of a specific tolerance. The program in that case would say, for even though this column above sits partially on the column below, the axial force we would use is whatever axial force is calculated for that column. We would not take a deduction between the upper and lower in this case, because these points, I'll call this point A and this point B, those are outside of a tolerance in the X and the Y directions. So that's how that's handled. And then the upper column would actually be looked at as a planted column. So this column we would check punching for the upper column, for example. If this was done in single level mode, we would actually check the punching, even if it's calculated globally, and you have this condition, and then you run punching shear. This column, that's the upper column, this column, that's the lower column, these would actually be checked individually. Typically, if we ran punching from a global analysis and they were stacked, really only the lower columns are being checked at the level that we're checking them at. If they're offset like this, then the upper and the lower would be checked, and the axial force in the upper would also be used for that particular column, as well as its own moments. So this is considered a planted column in this case, and this is exaggerated. But if you have some column, let's say this is brought in from Revit or maybe a conversion from a CAD file, and there's a tiny gap between the two centroids, then there is some tolerance that we look at, and the program would treat this similar as if they're stacked concentrically. If you have any questions about anything we've covered today, please contact us at adaptsupport@risa.com.